kinematics equation that I derived some time ago. Okay, we'll use that idea, but here now particles is launched at certain height at the edge of the building, right? And it goes up and down. So let me try to draw the situation. Okay, let me draw it this way. Not as nice as I want it to be. What a way to start this, right? Okay, but I can move this. Okay, so say this thing. I'm gonna draw the building right here. I'm gonna move this thing to the left just a little bit. I think that's about good. Okay, so I'm gonna draw the building right here. This is the building, and that height is 10 meters high at the moment. So far so good. And then we throw this thingy with upward velocity, and I'm gonna call that V, not original, to be 30 meters per hour. For 30 meters per second. So far with me, so you see what's going on here? Okay, I'm gonna move that thingy a little bit. And then arrowhead belongs right there. And then this thingy will go up somewhere to the maximum, and what goes up must come down, but then barely miss the edge of that building and then hits the ground right there. Is the motion that we have so far. You understand the situation, the way it reads? Okay, now I'm going to graph that out in time versus height. Okay, when we graph out, we start with some kind of original height, y-intercept. Then it's going to be an upside down parabola now, isn't it? Right, now let's not screw this up. This is not a projectile motion, okay? This is just straight up and down motion that was stretched out and plotted over time. You get it? So do not mix these two things up. So far, do you understand what's going on? Okay, I'm gonna rederive that vertical motion of the Newtonian kinematics here. Okay, so here we go again. G, acceleration. Okay, acceleration function in this case is negative g in meters per second square. With me? And that's the only thing we have. Then we take an antiderivative. If you take an antiderivative, you get this, right? Then do we pick up some unknown constant? In physics, we know that is the original launching velocity, but let's just use calculus to get exactly the same expression. This is where we use initial condition. Initial condition is V, originally when time is equal to 0 is 30. And then we substitute that in. With me? So what we have is this side becomes 30. And this thing becomes 0, right? T is equal to 0 plus C. So that gives us that C is equal to 30. So far with me? Now we plug it back in, so our V as a function of time, and in physics they usually write this first. And G is 9.8, by the way. You with me? Okay. Now, in order to find the height, the position, vertical position function, we take another antiderivative. So this becomes 30t minus ng t squared according to the power rule. Then, of course, we have to put 1/2, right? So that this thingy comes down and multiplies and cancels, eh? Okay. And then we pick up another constant. Let's call that d. So far with me? Now, our initial condition there, y originally is equal to 10 meters, eh? And we substitute that. So the left-hand side becomes 10, and the right-hand side becomes 0 minus 0 plus d, eh? And that tells you d is equal to 10. So far with me? Okay then. So finally, so we have a height function. Y of t is equal to, and let's put this thing first, plus 30t minus 1/2 gt squared. And the 1/2 g is 4.9 then. So far, so good? Okay, now we are ready to answer these questions. Okay, so let's do A here. A. We have to find the maximum height. Let's just look at this thing. Maximum height is right there, isn't it? And I'm going to call this point T1. How about that? We need to find what time that happens. Okay, now this is our regular maximum problem from calculus now, isn't it? Physically, that's the, well, it has to stop. But you notice that the slope has to be 0 right there? Right, so at maximum, why does this computer not respond to me? See, at maximum, your slope, right, y prime of t, but what is y prime of t? That is v, isn't it? Okay, that thing is this one right here that we calculated earlier. Right? Okay, that thing has to be 0. So it makes sense mathematically because the derivative must be 0, right? It has to be flat. The slope has to be 0 here. But physically it makes sense because whatever goes up has to stop before it comes back down now, doesn't it? Good? Okay, now then that will give us t is equal to 30 over g, 9.88. Using squiggly equal to now, remember squiggly equal to? This is what I'm calling T1. And if you punch the calculator, you get 3.061 to how many digits?
6.
6 with a squiggly equal to. So far so good? That's when it happens. Now we have to plug it back into where? We have to plug it back into this function, right? Watch the notation. And you punch the calculator, and that function is right here. This thingy. Isn't it? Good? Alrighty then. And you're supposed to get, let's see, 55.918367. Any questions so far? Are we good? Okay. Now, B. Let's do part B. Let's do part B in green. On the ground, it's like what we have to do is find the velocity of the particle as it hits the ground, right? So on the ground, what do we know about on the ground? You see that this height is equal to 0. You know what I'm saying? So we are setting this whole thingy is equal to 0. Now, this is where the program comes in handy because quadratic formula with that, it's like, it's a lot of work. And there's still like button punching error with a slash and all. Watch that video. I already uploaded the video on how to program your calculator. So it's just like your program, your app that you created will do it for you. Mighty convenient, okay? So if you do that, your T, and we'll call that T2. And that's this point right there, isn't it? T2 is supposed to be squiggle equal to 6.4 4.39377 seconds. Always write down the unit whenever you're dealing with time or anything. If you're given a unit, you always give the unit. So far, so good. Now, then, your velocity as it hits the ground. So from there, your velocity, and you plug into T2 into this thingy right here up there. You get it? Okay, that is supposed to give you negative 33.1. Is that 0 or 6? I can't read my own handwriting. 105891 meters per second. Somebody quickly punch that into a calculator to verify if that is 0. This digit right here is 0, not 6. My own handwriting is a little weird on the Dropbox note, and I'm going to replace that note with this one.
Yeah.
Okay, good. Do you have any questions? Now I'm going to copy the thingy that I graphed, thingy, create it in here. Okay, this is from my TI 84. I'm gonna just insert it right there. How about that? Jumping off the 10-meter high diving situation platform. So first she just steps off and then hits the water, right? So what speed, what velocity is she hitting that water? Okay, so let's do A first. So in situation A, let me draw the picture. So here's a platform and here's the water. And then she's just, boom, is the case now, isn't it? Okay. Are you good with just me starting with this thingy? This equation that I derived in the class? Are we good with this? Okay, let's just think about this. This is y naught, right? Which is equal to 10 meters now, from here to here. And then initial velocity, she's just stepping off, so the initial velocity is equal to 0. So far, so good? So in our situation, our equation becomes this. Have your calculator standing by to do quadratic formula or otherwise calculation. This is equal to 10 minus 1/2 gt squared. And g, of course, is 9.8, right? So this is now 4.9 t squared. So far, so good? Are you with me? And this point right here, at that point, your y is equal to 0, right? That y didn't turn out. This y is equal to 0. So then setting it to 0 and solving for this t, I'm going to call it t1. What do you have? Okay, useless children, you should get 1.428571. You don't even need a quadratic formula for this one, but okay. Now, then we are supposed to plug this thing back into the velocity equation. So what is our velocity equation? I'm going to do that with a blue color now. Our velocity equation is v naught minus gt. You remember this from yesterday's example? Right? But v naught is equal to 0 in our case. So this is equal to 0. So it's just negative gt. So plugging in our t1. And then you should get negative 14.000000. How about that? Very good. Okay, now part B. Let's do part B. Going back to red. So part B, now she jumps, right? So situation has changed a little bit. Here's a platform, and here's water underneath. She has the initial velocity upward. Okay, and that's 2 meters per second. I didn't mean to put that thing in there because I'm gonna, how about that? Okay, now then she actually goes upward initially, changing that color. And then splash right there. You get it? So that's the new picture now, and everything else stays the same. Y naught is equal to 10 meters per second, or 10 meters per second, meters. This way. Good? Okay, let's do this. Now, but nevertheless, our equation now changes. Y, this thing was 10. Now, see, remember up here, this was 0 in part A, but now we have 2. So plus 2t minus their 4.9t squared. So far so good? And then at this part right here, your y, the height has to become 0 because y is equal to 0 at the water level is what we are assuming, right? See, y is equal to 0 at this level. Height. Now, well, this time activate the program that I taught you, and then we solve it. So this t, I'm going to call it t2, is 1.647157 seconds. Okay, now let's figure out the velocity now. Velocity, which is v naught minus gt. Now, v naught is no longer 0, it's 2. So what we have is our velocity is 2 minus 9.8 t. You get it? Now plug it in t2. You're supposed to get negative 14.142139. How about that? So it's slightly more, well, slightly faster compared to this original one, because she has to jump up. So effectively she's falling. It's the equivalent of her stepping off from that height, whatever that maximum height is. You get it? Okay, now don't be getting rid of this negative sign. You keep the negative sign, it means downward.